All right, today I'm going to talk a little bit about physics in general, and it's even more than physics. It's just sciences. Even if you think about biology, the same rules or the same patterns obey in biology. It's not. We don't have mathematical tools appropriate for description of biology in such a neat way like we do it in physics, because physics is so simple. Physics just deals with the simplest part of nature. Well, it is a subject which describes the behavior of matter and its interaction on the most fundamental level. So we don't think about psychological states of animals or people. We just think, well, what are their dimensions, how they interact in order to move their body from one location to another location, and this type of aspects of human life. And a lot of other disciplines are based on physics. Practically, actually, every discipline has some elements of physics in it. If you understand principle of physics, it will help you comprehend your engineering classes much faster than if you don't know those principles. Let's take a look at the structure of physics. In other words, what actually does it do? How does it describe nature? Well, first of all, the purpose of physics is to describe what happens around us, and what is around us is called nature. So we in physics describe nature. Therefore, it has to be based on whatever we observe in nature. First, we have to observe nature, we have to recognize certain patterns in nature, and then we can develop physics, models. And I brought here a cartoon which is probably 70 years old, but really I like it because it explains how physics really what physics does to the nature. So we think about some aspects of nature. Although, as I mentioned yesterday, we can also think about aspects of economy, for example, so things which can happen on Wall Street. You can also relate one quantity to another quantity over there as well. We introduced various quantities like Dow Industrial Average. All right, so let's say that I have a certain physical quantity and another physical quantity. Probably the easiest one which would come to your mind is, for example, that here we have time, and here we have, let's say, component of position or speed. Well, and for a certain item in nature, we, let's say, find such a plot. We have to observe first nature. After we observe nature, we can identify certain discernible patterns. So, for example, that these points are along the contour of those two elephants. Well, then these two elephants become a description of nature. Rather than remember where these points are, we just have to drop those two elephants. And what now we can do with this, well, we can predict, because we can now create data points in between, which is called an interpolation. We say that, well, this quantity still follows the same patterns, so we can supplement data points in between. They are not obviously now data points based on the observation of the nature. They are prediction from a description, from a, it will be most likely from a mathematical model. So in between we can interpolate, and we can extrapolate also to predict something outside. After, I mean, let's say if this was time, so it will be after, let's say that this corresponds to today, so we can predict future. We can also predict, I didn't draw it, but we can predict the past. This is how we, for example, came to the conclusion that there was a Big Bang, and what will happen with the universe in the future, because we extrapolate the information which we have now. This cartoon was made by a famous Indian scientist. His name was Raman, Chandrasekhara Raman. And if you are going to study chemistry, you will hear about him a lot. Probably in biology as well. I know that in biology there is a professor who has a Raman system. He discovered a certain type of radiation coming out from molecules and substances, which is related to forces between the atoms constituting these molecules. All right, now one thing which I have to be clear of is that physics does not explain anything. Physics just describes. We don't know why we have gravity and why we have four fundamental interactions. We don't know why our space is three-dimensional. It simply is. And whatever nature provided, physics describes. It develops from those descriptions. We can predict. I mean, when we say that we understand how something happens, it means that we see logic. We see relationships. We recognize the pattern, but we don't know why that pattern occurred in the first place. So remember that physics does not explain things, it describes them. And in order to describe those things, well, we develop various things in science. So we introduce various concepts, relate the concepts, and then find out or postulate various things about the concept, and this way we create abstract models about nature. Actually, we create those models in such a way that you cannot get rid of them. The way you are thinking, even now, you are thinking in terms of models. And let me bring you an example, right? You have no problem with the fact that it is what time is it now? 8:13. What does it mean? Why don't you have actually a conversation with each other now? What does it mean that it is 8:13? And can you think about it a different way? That it is 8:13. Why don't you introduce yourself to each other, start talking, and have a discussion. So go ahead. All right. Now, may I have your attention, please? All right. Now, think. How would you describe time if you didn't use this abstract concept as numbers? Yeah, because we are so accustomed to assign a number to time that we don't even know how to describe it a different way. And now, for example, like our class lasts 20 minutes. If I couldn't use word, a number, how would you describe how long is the class? See that? I mean, you have very hard time now to get rid of numbers. But numbers are abstract concepts. It's our invention. We invented numbers to describe things. We learn how to manipulate them, and now the entire nature is based on those numbers. All right. Here I give you an example of a description. I mean, with this one, you will probably see it better how to use numbers and what they really do to nature. Let's think about a very simple phenomenon like diluting a solution. And rather than thinking about diluting a solution, I will think about Pepsi and water. What kind of fluid I got if I mix a combination of Pepsi and the water? So if I mix Pepsi with Pepsi, I'm going to get Pepsi. I will still taste Pepsi. If I add water, actually, when we drink Pepsi, half of it is water anyway. Yeah, because ice cubes, when the ice cubes melt, they release a lot of water. But we still have Pepsi, because it is still that solution. So if we mix Pepsi with water or water with Pepsi, we will get Pepsi. The only way that we don't get Pepsi is if we mix water with water. So I can think about that this is a table of mixing. Now, this table of mixing actually is very similar to this table. And now, what is this table? Yeah, this is table of numbers, but it represents a certain operation. Multiplication, correct. Yes, so 0 times 0 is 0. 0 times 1 and 1 times 0 is 0. And the only time that we get 1 is if we multiply 1 with 1. So what we do in science, we assign now, let's say, Pepsi to number 0, water to number 1, and we perform operations on this table to predict what happens in nature. Do you understand that? This is what really we do in science. Very often we could not even think about this table at all. In any other way than over here. One of the experiments which you are going to have in the lab will be recognizing the character of a certain physical quantity which describes interaction, namely force. You will analyze properties of forces. And when we think about forces, because what is force? Force is just a push or pull, how one object pushes or pulls another object. But rather than thinking about push and pull, well, we introduce a concept which is called force, and we will say that it will have a certain magnitude and certain direction, and you will think about force more like an arrow than really something which is unimaginable. I cannot imagine really force other ways than an arrow. However, obviously force is not an arrow. It is an item from the model. And actually, when I have this arrow, because we can create these abstract models in different ways. It doesn't have to be always the same way. So I can think about over here that I have arrows and imagine forces in terms of arrows. I can think about triads of numbers, sets of numbers. And we will learn actually both. We will learn about a number of physical quantities which are, linked to sets of numbers or arrows. We will see in the future that these quantities are referred to as vectors. This will be subject of tomorrow's lecture. Well, later even. I'd like now to go a little bit into the history of physics. Historically, actually, physics developed in such a way that we have a part of physics which we refer to as classical physics, and practically in this class we will study just that, only classical physics. Classical physics is the physics with which we are the most accustomed, and classical physics is the one which is sufficient for any engineering, well, not maybe any engineering, but most of the engineering problems. Only those of you who are in electrical engineering, you can encounter problems which are inconsistent with classical physics, because classical physics is just a model of nature. And if we have a certain model, what is it supposed to do, by the way? What is the purpose of the model? To do what? Predict outcomes. Yeah, it is to describe nature in such a way that you can extrapolate or interpolate. Correct. So it can happen, yeah, because I mean, in the history we were looking at various aspects of nature and developed certain descriptions. Well, from time to time, somebody did an experiment which was inconsistent with the prediction. What happens when an experiment is inconsistent with the prediction? Well, we repeat it to verify if this is true. I think that the largest number repetitions for an experiment was done on an experiment designed by two American scientists, Michelson and Morley, at the beginning of 20th century, well, just before, or at the end of 19th century. We develop a sneaky way, they develop actually a very clever way to figure out how fast Earth is moving. In other words, they actually built a speedometer for Earth. The problem was that no matter where they put the speedometer, they always found the same speed. Or even more important, velocity, because they were also considering which way. Yeah, so we figured out, well, if we are traveling one way in space, half a year we are going to move the other way. So they wanted to figure out, well, how fast they move. And with this device, they were supposed to be able to measure measure it. And well, they predicted how fast we should move one direction and another direction, and just wanted to measure it. Really, the experiment was even more important about finding the road. Yeah, where that road is. Yeah, because right now, are we moving or are we not moving? Are we? What are we doing? Are we moving now? Oh, who thinks that we are not moving? Are we moving? Are you moving now or not? Well, it depends on which road. Yeah, because if we think about our classroom, we are not moving. Well, but the entire classroom actually travels that way, and pretty fast. Pretty fast. In 24 hours, we will move around the entire circumference of the Earth with entire classroom, right? Because, I mean, we are spinning this way. We are spinning eastward. So on the surface, if I think about the surface, an abstract surface around Earth, we are spinning in it. Well, but who says that that surface is the most important reference in the universe? Well, we are also circling the sun. So depending on this, which road we are looking at, we are moving, we are not moving, and we are moving in various directions. All right, yeah, so coming back to Michelson-Morley experiment, they failed actually to determine confirm the predictions from the model, how we are moving on that road, which is called space. Well, what's the consequence? What's the conclusion then from the experiment? I mean, we were so stuck in believing this classical physics that this experiment was repeated 100 times. Well, eventually we had to come to the conclusion that classical physics is wrong. And this is the subject which I'm going to help you to learn. You will be learning a model which doesn't really generally describe nature. However, it describes very well aspects which are necessary for engineering. Therefore, we did not abandon them. We just have to know the boundaries in which we can use the models and still predict how to design things, and are they going to work, and so on. So the only engineers which can have problem with classical physics are electrical engineers, because there are certain elements like tunneling diodes, for example, and, well, electronics. A lot of elements in electronics actually requires broader model, which is based on quantum physics. And particularly now when we go into nanotechnology, this requires quantum physics. But classical physics includes classical mechanics, which is the study of motion. And actually the study of motion does not include description of this object, how the object moves, but what causes it. So mechanics includes both kinematics, which says where the objects are and how they change their position or the arrangement. I don't know, yeah, because position is already an abstract concept. But also what causes it. So it will also include interaction. Mechanics also includes a section which says how one object interacts with another object, because actually without this interaction, nobody here would be able to leave the room. We walk because we understand, well, we do it instinctively, but if we think about it, we have to follow laws of mechanics in order to get to the class, get out from the class, and so on. Now, the next one is thermodynamics, which is study of energy transfer. It refers to systems which are too complicated to follow its motion. Yeah? Because, for example, my body is composed of a huge number of atoms. So, really, my position, in order to precisely describe where I am, I would have really to say where each atom of my body is. Well, who cares about it? Definitely not biologists. And I don't either. So rather than thinking about individual atoms, we think about an object and say, well, this is just a bunch of atoms. However, macroscopically, well, it interacts somehow with the surrounding. This system, for example, eats sandwiches, and that sandwich disappears somewhere, and something happens to that system. We don't really care precisely where each atom of the sandwich went. We care what was the combined effect of that sandwich. So we introduce this concept of energy, which doesn't care about, well, I mean, we have this concept for individual atom as well, but it's more important for the total value. So thermodynamics describes behavior of relatively complicated systems. Well, there was a time that that electricity and magnetism were separate, but by eventually Maxwell actually combined, put all together in a nice set of equations called Maxwell's equations, although each equation in the Maxwell's equations has a name of another scientist who first saw the relationship. However, he recognized that these equations are sufficiently important so that they should be put together. So electromagnetism involves electricity, which is about transport of charged particles, about magnetism, which is a certain type of interaction which occurs among charged particles. And optics is also part of electromagnetism. Optics is just a separate science about light, and we developed this science because it is important for us. Why? Because we have eyes. If we didn't have eyes, then we wouldn't probably develop optics at all, because why would we describe a nature which we don't see? Although sometimes we do that. Here are some of the famous people who made kind of big steps in science. Probably you recognize this one. Why don't you consult with each other? Who is this? Galileo, correct. This is Galileo. Who is that? Newton, correct. Oops. Oh. This person is Gay-Lussac. I don't think that heard about him. He contributed a lot to thermodynamics. So obviously this one has to be Maxwell. Yeah, he combined laws in electromagnetism. And classical physics ruled actually our understanding of nature until the end of 19th century. At the beginning of 20th century and at the end of the 19th century, we were finding more and more evidence that classical physics is inconsistent with nature. We were finding experiments which contradicted it. So in 20th century, we developed a certain branch of physics which is referred to as modern physics. And I already think about modern physics that it became pretty ancient, because it is already more than 100 years old. But probably for another 300 years it will be called modern physics. It includes relativity, which is a theory of what happens at high speeds. And, well, probably, I mean, this is kind of common knowledge. I mean, probably you heard about it. The most confusing concept with relativity is actually time. The way, and it's not time as the phenomenon in nature, but the way we assign the values to time. It happens that well, the way we assign values of time, well, it has to be, it is done in such a way that we cannot exceed, we have speed limit in nature. We cannot exceed speed of light. Speed of light is the fastest speed with which an object moves. Well, I think that at this point you see no problem with it, but let me actually bring or ask you for us to think about something that will well, you will see kind of a paradox. Yeah, because let's say that if I walk in this direction 1 meter per second, and I toss an object, I'm not going to toss this mouse though, and I toss an object with speed 2 meters per second forwards. It will fly away from me with speed of 2 meters per second. How fast would you see this object to move? How many? 3 meters per second. Correct. Now, if I drive a car and it is dark outside, let's say that I drive the car with speed of 55 miles per hour in this direction, and at a certain point I decide to turn headlights. When I turn headlights, the light is going to escape from me with a certain speed. Now, will you see this light moving faster than I or not? Well, who believes that you will see it faster than I do? This is what you would predict from classical physics. But it's not true. I will see it moving exactly with the same speed as you do. And here is a problem. Yeah, because when you just hear, well, there's a speed limit, well, so what? I mean, everywhere we have speed limits. And we get tickets for not obeying them. All right. Now, when we analyze what happens in nature, if we take a look at the microscopic world, classical physics also fails. One of the things which you maybe heard, I mean, particularly if you are chemists, that for example electrons in atoms don't move in an arbitrary way. They have particular orbits, right? Have you heard about that? That they move, even if we introduce concept of those orbits, electrons cannot move in an arbitrary way. They will move only on particular orbits. Or I mean, particular orbits will have particular radii. This was Bohr model, which we abandoned already too. And right now we rather than orbits, we have, those of you who are chemists, why don't you shout? Not orbits, but also starts with O. Orbitals. Now, orbital is really a confusing concept, because rather than saying how electron moves, we say that it is everywhere simultaneously. And actually, well, think about it, does it make sense? I mean, what would happen if I, for example, disappear here, disappear from you 1,000,000 times a second and come back, and pop out here. So I pop out and disappear, pop out and disappear, 1,000,000 times in a second. And every time when I leave, I leave for 1/10,000,000th of a second. How would you see me? And let's say that I'm just dropping by to Mike's for 1/10 of a million of a second. How would you see me? How? Just like I am. Right. I will look exactly the same way as I am. And actually, you are doing it from time to time. Whenever you go to see a movie, for example, you have to realize that most of the time you look at the blank screen. The screens just pop out one after the other, but in the meantime, there's nothing on it. It's blank. However, we see a certain reality on the screen. All right, and here are some people actually which made big steps in modern physics. Well, I wonder, you know this. I think that you know this guy. It's Albert Einstein. Okay, now do you recognize at least one more person here? Who is the next one? Yeah. All right, so this one is Max Planck. Planck's constant, for example, is based after him, and Planck's constant actually makes this quantization of energy. This guy is Louis de Broglie, and he was a person who came with the idea that all matter has particle wave duality. So we can look at waves as a beam of particles. Well, we were doing it actually before him. So for example, if we look at the beam of light coming out from the projector to the screen, already Newton came with an idea that this is a beam of light particles. And I think that you even heard the word for light particle. Do you know what do we call what is the name of light particle? A photon, correct. So Newton already thought about light, that it's a beam of photons. Later on we figured out, I mean as a humanity we figured out that no, it's a wave actually. Now we believe that it's simultaneously a wave and a beam of particle, and depending on in various situations it behaves one way or the other way. Where de Broglie actually came with an idea, well, if we have something, well, if light behaves that way, so if we shoot a beam of electrons, maybe we should look at that it's a wave as well. And so he came with an idea that everything is a wave. We are waves too. All right, and Erwin Schrödinger actually made a big step forward with formalizing. He wrote an equation similar to what Newton did in classical mechanics. He wrote an equation which allows one to predict what will happen with the system in the future. Now, because of simplicity and accuracy of mathematics, because math is really simple. I mean, if we're not simple, we probably wouldn't invent it. Mathematical models are used to represent nature. And common mathematical concepts which are used in physics are numbers. We use a lot of numbers. Sometimes we use sets of numbers. And sets of numbers, well, they are very closely related to those arrows and are referred to as vectors. We can use even larger sets of numbers. These are called tensors, and even more of them. These are functions. So in a function, we already have an infinite number of numbers, and even not the numbers, but operators. In quantum mechanics, you will see something like this. Well, since we have to assign numbers to various, or sets of numbers, we have to develop a certain procedure. That procedure is called a measurement. So, in a measurement, we assign numbers or sets of numbers to physical quantities. That procedure is called a measurement. And every measurement is based on comparison of a given element to an element which we choose as a standard. Now, the way we assign numbers are not unique. Yeah, because, for example, think about your height. Well, you can assign a number which is, let's say, around 6. You can assign a number which is around 180. Yeah, because for example, for me, I can say that my height is 6, and I can say that my height is 180. I can even say that it is 1.8. Probably, at least, there were some of you who agreed with each of those numbers. So I'm 6. My height is 6, but then I have to say in what standard. Yeah, how do I identify what do I choose for standard? By adding a unit. So I am 6 what tall? 6 feet tall, correct. Now if I'm 1.8 of what? Of a meter, correct. So by choosing appropriate unit, I can assign a number, different numbers. Now, what you will have to do as engineers, you will have to make sure that you stick to the units. And it will work. No matter which unit you choose, you can predict the future, or you can predict the past. From time to time, however, well, one engineer will come to you and he or she will tell you a number describing certain quantity using a standard which is incompatible with your thought. What do you have to do then? you have to convert the units. And in order to convert the unit, you have to know so-called conversion factor. You will have to know how many of one unit are in another unit. Let's take a look at an example. Let's see how many minutes is in 1 microcentury. Well, 1 century corresponds to 100 years. So conversion factor between years and century is that 1 year is 100 of a century. Oh, actually, this is conversion factor as well. Now, 1 year converts to days by a factor of 364. 1 day converts to hours by a factor of 24. And 1 hour converts to minutes by a factor of 60. 1 microcentury. Micro is a prefix which says that this is 10 to minus 6. So, and actually I copied this one, 10 to minus 6 on both sides. And here I'm writing. Well, 1 century, it's 100 years. So actually I should write over here also 1 times 100 over 1. Then conversion factors between days and years is 364. Hours and days is 24, and minutes and hours is 60. Now, when you convert, actually, conversion factors are always expressed as a fraction of 1 unit with respect to another unit. However, conversion factors refer to units which are used to describe the same quantity. So like over here, all of those refer to time. Right? Now, it has to that mathematically they cancel out. Yeah, I have years here and years here. These cancels. Days and days cancels. Hours and hours cancels. Then I have an expression of 1 century, 1 microcentury in terms of minutes, and I can recognize it. I mean, if I perform the calculation, 1 microcentury will be 52 minutes, which means what? That every time when you come to this class, you spend about 1 microcentury. Now, since this clock is not working, I even don't know what time is it now. Oh, it's exactly 8:52. So I think that this will be the right time to end the show. Wait.